Hello everybody and welcome back to another Algebra 2 lesson. Today we're going back in time once again to Unit 5, where we were talking about rationalizing roots. So when we last discussed, this should say radical, not rational, meaning there's a square root in them, or a cube root, or a fourth root, we mentioned three rules that all roots must follow. You can't have perfect nth powers as factors other than 1. Basically, if you've got the square root of 4 squared, simplify it. No radicands could contain fractions. So when we had fractions, we split our fraction up into 2 different roots. But the third one's the most interesting one. No radicals may appear in the denominator of a fraction. In Unit 5, we learned a little bit about how to rationalize the denominator. So, if we're dealing with square roots, this is pretty easy to do. We just have to multiply the numerator and denominator by that square root and watch what happens. So if we're left with 5 root 2, 5 over root 2, the rule is we can't have a radical in the denominator, so we have to get rid of the square root of 2. To do that, we learned that we can multiply the top and bottom by the square root of 2. The reason why this works is because square root of 2 over square root of 2 is just 1. We're just multiplying this by 1, but in a way that makes them self-simplify. What's the square root of 2 times the square root of 2, though? 5 times the square root of 2 is just 5 root 2, but how could we write the square root of 2 times the square root of 2? We could write it two ways. Either the square root of 2 squared, since there's 2 copies of them, we write it as a square, and then the square root and the square cancel out, giving us just 2. That's why rationalizing works. Rationalizing this way works because if I have 2 copies of the square root of 2 being multiplied together, the square root and the square cancel out. Because they're inverses, this is why it works. So in example 1, we're asked to simplify a couple expressions and rationalize any of our denominators. So let's take a look at A. We have 3x over the square root of 6. So this is a denominator that needs to be rationalized. We need to multiply this by something that'll turn it from a root into not a root. Well, to get rid of a square root, we need 2 copies of it. Why is that? Why do I need a second copy of this? Well, because if I was to write this out, 3x times the square root of 6 is just 3x root 6. But the square root of 6 times the square root of 6, there's 2 of them now. That means we could write it as the square root of 6 squared. And a square root and a square cancel out, leaving us with just 3x square root of 6 over 6. Now, we should ask ourselves, is there any more simplification we can do here? Because there is one last thing. Notice that 3 and 6 can both be divided by 3. We just need to simplify our fraction. 3/6 is the same as 1/2, so I could just write it all over 2 instead. If I divide 3 by 3, I end up with 1, so I can just write it as 1x or x. The square root of 6 sticks around. 3x root 6 over 6 simplifies to x root 6 over 2. Well, what if we tried looking at b? Similarly, we would want to try and rationalize the denominator. But be careful. We don't mind this 4 being here. We do mind the square root of 2x. Before we rationalize, we should always check to see if anything else can simplify. In this case, negative 16 over 4 actually ends up just being negative 4 over root 2x. Can you figure out how to rationalize this one? Pause the video and try it out. Hopefully we see that rationalizing this would require us to multiply by the square root of 2x. The reason is, since there are 2 copies of it, and it's the square root, this will be like the square root of 2x squared. Up here we'd have negative 4 root 2x, and the square root cancels out with the square. We'd end up with negative 4 square root of 2x over 2x And even more cancels out. This is negative 2 root 2x over x. For problem C, notice how we have a big square root. Now, rule number 2 is no radicands can contain fractions. So let's first split this up into two different square roots. The square root of 2x over the square root of 7. Now, when we rationalize it, we would multiply both the top and bottom by the square root of 7, because again, we need two copies to cancel out a square root. This would end up with the square root of 7 squared over the square root of 14x. This is just going to give us the square root of 14x over 7. Done. So rationalizing square roots is pretty easy. Just give it another copy. But can we apply the same rules when we're rationalizing other roots? What if we were trying to rationalize the following? 7 over the cube root of x. Well, our first instinct might be, let's just multiply it by another copy of the cube root of x. But this quickly doesn't work. Why? Well, if we try this out, 7 times the cube root of x is just 7 cube root of x. But what's the cube root of x times the cube root of x? Well, since there's two copies of the cube root of x, we could write it as the cube root of x squared. Does anything cancel out? No, it doesn't. We didn't successfully rationalize our denominator. We would say this is not rationalized. So we need a new approach. Since we end up with the denominator of the cube root of x squared, it doesn't cancel out. Why? Well, because in order to cancel out a cube root, don't you need a cube or 3 copies of something? Instead of giving us 2 copies, we will need a total of 3 of them. So actually, what we'll end up doing is, we should multiply by 2 copies of the cube root of x. What that'll do is, that'll leave us with 3 in total, and the cube root and cube cancel out. So follow along with this example. Instead of just multiplying by the cube root of x, we multiply by the cube root of x squared. Why would we do that? That looks crazy. Well, because now count up how many cube root of x's we have. Got 1 here, 2, 3 here. I have 3 copies of the cube root of x, or cube root of x cubed. Since a cube root and a cube cancel out, we've done it. And all we had to do was multiply by something crazy, which is the cube root of x squared. Another way to think about it is to rewrite these as rational exponents, which might make it a little bit easier. So recall that you can rewrite anything, any radical, as a rational exponent. Let's say I was rewriting the cube root of x squared. And the square could be on the inside or the outside for this purpose. Doesn't really matter. Well, we would rewrite it as x to the, your index becomes the denominator, so this is something over 3. This is to the second power, this is x to the 2/3. It can help us to see why we're doing what we're doing if we write everything as rational exponents. Think. If we're starting with x to the 1/3 power, this is what we're basically starting with here. If we're starting with this, x to the 1/3 power, what exponent plus the 1/3 will make 1? Well, 1/3 plus 2/3 is 1. So we can instead think about it as this. 7 over x to the 1/3 power. We need 2/3 more to make 3/3. We multiply both the top and bottom by x to the 2/3 power, because x to the 1/3 times x to the 2/3 is x to the 3/3, because of our exponent rules. And 3/3 is just 1. So that's why this rule works. Some students will prefer to think of it as, how many copies of the cube root of x do I need? Some students prefer to think, what other part of the fraction do I need to cancel out? It's up to you. So let's take a look at these next examples. Here I've got 8x over the cube root of y. So to rationalize this, we need to think for a minute. To cancel out a cube root, how many copies do I need? 3. If it's a cube root, a cube will cancel out. I have 1 copy here. How many more do I need over here? I need 2 more copies. So we write that as the cube root of y squared. And again, the square can go inside or outside. They're both equivalent. The cube root of y squared cancels it out, because now there's 1 copy plus 2 copies. That makes 3 copies of the cube root of y. We write it as the cube root of y cubed, and on top we have this craziness, 8x times the cube root of y squared. Just for simplicity's sake, I'm going to write the squared inside. Makes it look a little bit neater. And what's the cube root of y cubed? They cancel out. We get just our answer. On the bottom, we're left with just y. And on the top, we have 8x times the cube root of y squared. Done. Wasn't so bad. Let's see the next one. Here, what do we do if there's one big root? We can split it up. So we take it as the 4th root of 16 over the 4th root of 9. And the 4th root of 16 is just a number. That's just 2. Well, if I'm talking about a 4th root, how many total copies do I need to cancel out a 4th root? I need 4 total copies. How many do I have? I have 1 copy of the 4th root of 9. So, how many more do I need? If I need 4 copies and I only have 1, that means I need 3 more of them. So to do that, we're going to multiply by the 4th root of 9 cubed. Well, the 4th root of 9 times the 4th root of 9 cubed is the 4th root of 9 to the 4th power. So we got it. We got those two numbers to match. But up on top, we have this crazy expression, 2 times the 4th root of 9 cubed. Insane. On the bottom, we have the cancellation. So this is just 9 on the bottom. But this time, there is more simplification we can do. Because 9 to the 3rd power is actually just a number. What is 9 times 9 times 9? That's going to be 729. So we can write this as 2 times the 4th root of 729 over 9. Now, is the 4th root of 729 a perfect 4th? No, it's not. But sometimes on a test, you might see your answer written like this, or like this. Or it could even be written as a rational exponent. It could be written as 2 times 9 to the, that's a p, 2 times 9 to the 3/4 power over 9. And here, that might be something you see. So just keep in mind, there's different ways of representing the same stuff. What I'd like you to do is I would like you to try C. C is a tough one, but I'll give you a hint. How many copies of the 5th root of x do I have if I see the 5th root of x squared? I'd like you to pause the video here try this problem out for yourself. I'm going to reveal some of the work down below in just a moment. So pause the video and try it out. How'd you do? From looking at this, we see that we have 2 x's. And if I wanted to cancel out with the 5th root, I would need 5 x's. So I give it 3 more. The 5th root of x cubed is what you need, because a cube and a square, when you add them up, makes 5. That was a tough one, but this should be your final answer. All right. Last but most certainly not least, we have this idea that we didn't really talk about much, but we have used this vocabulary before. We have this idea of a conjugate. Where have we heard that word before? Well, we heard it when we were talking about finding the real roots of a polynomial. If I was to give you x squared plus 4 and ask you to factor it, you would say, Mr. Strager, this is not a difference of squares, it's a sum of squares, so how do we even solve this? And what we learned is this. When finding this, essentially try writing it as x squared plus 0x plus 4. We're trying to think of 2 numbers that multiply to make 4, but cancel each other out. And it turns out there's only 2 numbers that do this. Our answers to this problem are x minus 2i and x plus 2i. This was a little bit ago, but the reason why this works is because negative 2i times x and positive 2i times x will cancel out in the middle, make 0. Negative 2i times positive 2i is negative 4i squared, and I squared is negative 1. We talked about this in the sense that these 2 factors are conjugates of each other. When you have one, you must get the other. Think of it like that. Think of a conjugate as a pair of numbers that are tied together. And it's no different with roots. The conjugate of some radical is the same radical with a different sign. So if you have, for instance, 2 minus the square root of x, your conjugate is 2 plus the square root of x. If you have the square root of 20 minus y, your conjugate is the square root of 20 plus y. They're paired together. They're inseparable. And it turns out this is the only way to get rid of more complex denominators like the ones here. Let's see why we can't use our normal strategies. If I have 5 over 4 plus the square root of x, our normal strategy would be multiply the top and bottom by the square root of x. This would give us 5 root x over 4 times the square root of x is 4 root x, and the square root of x times the square root of x is x. I've made no progress. I've still got a square root of x in my problem. So this isn't going to work. Instead, I am telling you, the way to get rid of one of these more complicated denominators is actually to multiply by the conjugate of your denominator. So what's the conjugate of this denominator? 4 plus the square root of x. The conjugate is 4 minus the square root of x. And let's see why this works. First off, let's do the easy part, the top. Whenever you're multiplying just one term by a binomial, you can just distribute, like so. 5 times 4 is 20. 5 times negative square root of x is negative 5 square root of x. Cool. But what do you do when you have 2 binomials, like 4 plus the square root of x times 4 minus the square root of x? Both of those have 2 terms in it. This is where we FOILed, or used double distribution. We would do 4 times 4 for first, we would do 4 times negative square root of x for the outer two terms. We would do square root of x times 4 for the inner two terms. And we would do square root of x times negative square root of x for the last terms. So what's 4 times 4? That's just 16. What's 4 times negative square root of x? That's negative 4 square root of x. We need to make my fraction a little bit longer. What's the square root of x times 4? That's just positive square root of 4 square root of x. And what's the square root of x times negative square root of x? That's just negative x. Does anything cancel? Because I see a negative 4 root x and a positive 4 root x. That means our answer is just 20 minus 5 root x over 16 minus x. Done! Denominator rationalized. The reason why we have to multiply by the conjugate is because we have to have a way of getting rid of that middle term. They have to be the same. This provides us with a little bit of a shortcut. The shortcut is, if you remember your sum and difference pattern, you can go straight to that on the bottom. But as a reminder, the sum and difference pattern works like this. Anytime you have a plus b times a minus b, even if a and b are square roots, it's a squared minus b squared. Just square the first one minus square the second one. Let's see if we can apply that knowledge to b. So b, we have a crazy denominator, the square root of x minus the square root of y. But what's the conjugate? The conjugate is the square root of x plus the square root of y. So we multiply the top and bottom by that. 2 times the square root of x, square root of 2 times square root of x is square root of 2x. Square root of 2 times square root of y is square root of 2y. But in our denominator, we can use our shortcut. The shortcut is, we know that a minus b times a plus b is just going to be a squared minus b squared. So what's the square root of x squared? That's just x. And what's the square root of y squared? That's just y. Done. If you know the trick, this could be the easiest type of rationalizing you do. Finally, what's the conjugate of this denominator? We have 3 root x minus 6. The conjugate is 3 root x plus 6. So from here, when we multiply this out, 2 times 3 root x is 6 root x. 2 times 6 is 12. That's our numerator. Let's use our shortcut. What is 3 root x squared? Well, 3 squared is 9, and the square root of x squared is just x. So that first term is 9x. We put a minus sign, and then we put down, what is 6 squared? That one is just 36. With that, we are done. We should check to see if anything cancels out on the top and bottom, which actually in this case it does. I apologize. If we were to factor these, like we learned in Unit 7, we could write this as 6 times the square root of x plus 2 over 9 times x minus 4, and 6/9 does in fact simplify. We could write our final answer as 2 square root of x plus 2 over 3 x minus 4. Aha! But we are done. That's it for rationalizing different roots, everybody. I hope you've enjoyed this one, and have a great rest of your day.